So in today's lesson we're going to revisit a topic we've talked about before in class. When we were doing our differentiation work, we talked about rates of change, and one of the situations we looked at was displacement, velocity and acceleration all being linked to each other. And as a reminder of how they were linked, displacement, we usually use S to describe displacement, and then we were able to see from that we can get velocity and acceleration expressions, because our definition for velocity is that it's the rate of change of displacement with respect to time. So it's basically given as ds over dt. That means if I've got an expression for displacement, I can differentiate it and I'll have an expression then for the velocity. And likewise, the definition of acceleration is it's the rate of change of velocity with respect to time. So I can differentiate my velocity expression to get an acceleration one. So that's how we first looked at rates of change when we were doing differentiation. But now that we've done integration, we can now work backwards. Before we needed displacement to get velocity to then get acceleration, but now with integration, I can work back the way. If I actually start with an expression for acceleration, then I can get a velocity expression by integrating my acceleration with respect to time. And likewise, once I've got an expression for velocity, I can get an expression for displacement by integrating my velocity expression with respect to time. So that's how the displacement, velocity and acceleration are all linked to each other. So we'll have a look at a quick example now. We've got a question here that says the velocity of an object is given by the velocity is equal to t squared minus 4t minus 5. We're asked first to find an expression for acceleration and then an expression for displacement. So we'll start with acceleration. Thinking back to the sort of slide we just looked at, how do I get acceleration if I'm given velocity? Well, to get acceleration, I am going to differentiate my velocity expression. So all I need to do, differentiate this expression up here. So t squared becomes 2t, negative 4t, but differentiates to 4, negative 4, sorry, and we know the negative 5 in effect kind of just disappears. So there we go, we've now got an expression for acceleration of 2t minus 4, and it's as straightforward as that. Moving on to part B, this time we want displacement. Given velocity, how do I get displacement? Well, a wee reminder, if I want displacement, I need to integrate the velocity expression. So I'm going to integrate this expression up here. So if I do that, I integrate t squared, I end up with t cubed over 3. I integrate 4t, so I will end up with negative 2t squared. So power up by 1, divide by that new power. Integrate negative 5 to give me negative 5t. And when I integrate, because it's not a definite integral, I've got no limits here, I'm going to need my constant of integration. So I now have an expression for displacement, but this constant of integration doesn't really help me here. I need to know what that number is. And that's where these initial conditions then come in. So initial displacement is 3. That basically means when t was 0, when time hasn't started, the displacement is 3. So to calculate C, I'm now just going to put displacement of 3 here, time of 0 into here. So what we end up getting is we get 3 is equal to 0 cubed over 3 minus 2 times 0 squared minus 5 lots of 0 plus C. So we know then C must be equal to 3. So in order to get my expression for displacement, I now can change this C to 3, and that becomes my expression for displacement. So that's how we work with these rates of change questions. I've put together a past paper selection of questions. They are quite tough, but I think it'll be good practice for you just to get used to toggling between differentiating and integrating in order to solve these questions.